Let me ask you something. When you measure a distance, say from here to the door, you might use meters. And when you measure time, maybe you use seconds. Now, why do we use different units for space and time? Well, we do it because it's convenient. We're used to it. We walk around at human speeds. We live human lifetimes. And meters and seconds work pretty well for describing our everyday experience. But here's the thing, and this is where it gets interesting. Space and time aren't really separate things at all. They're parts of the same thing. We call it space-time. And just like you can measure distance in miles or kilometers, just different units for the same thing, space and time are connected by a conversion factor. That conversion factor is what we call the speed of light. Think about it this way. Suppose I told you I'm going to drive 60 miles. You'd probably ask, how long will that take? And I might say, oh, about an hour. Now, if you're used to thinking in terms of miles per hour, you immediately know what's going on. But imagine if I lived in a world where everyone always traveled at exactly 60 miles per hour. No faster, no slower, just 60. In that world, would we even bother having separate units for distance and time? We might just say, I'm going 1 hour, and everyone would know exactly how far that is, 60 miles. The 60 miles per hour would just be a conversion factor between our time units and our space units. Well, that's exactly what's going on with the speed of light. The speed of light, this number we call c, about 300,000 kilometers per second, is really just telling us how to convert between our measurements of space and our measurements of time. It's like the conversion factor between miles and kilometers, except it's converting between space and time. Now you might say, but wait, Feynman, things don't all move at the speed of light. I'm sitting here, not moving at all. And that's true, you're not moving through space. But here's the remarkable thing, you are moving through space-time. Right now, as you sit there, you're moving through time at 1 second per second. Sounds obvious, right? But think about it in space-time terms. You're traveling along a path through space-time, and all of that motion is in the time direction because you're not moving in space. Now here's where it gets really wild. It turns out that every object in the universe is always moving through space-time at exactly the same rate. Always. No exceptions. The total motion through space-time is always the same. When you sit still, all your motion is through time. When you start moving through space, some of that motion through time gets converted into motion through space. The faster you move through space, the slower you move through time. That's time dilation. It's not some weird side effect. It's the most natural thing in the world once you understand that space and time are connected and there's a fixed total rate of motion through space-time. And what is that fixed rate? Well, it's c, the speed of light. But now you can see it's not really a speed in the ordinary sense. It's more like a fundamental property of the geometry of space-time itself. Let me give you another way to think about it. You know the Pythagorean theorem, right? If you have a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. A2 plus B2 sub C2. Now that formula works in flat Euclidean space, but space-time isn't quite Euclidean. It's what we call Lorentzian. The formula looks almost the same, but with a crucial difference. CT2, X2, Y2, Z2 equals something that doesn't change when you switch reference frames. Notice that C sitting there in front of the time term, that's not an accident. That's not just unit conversion. That C is telling you something deep about the geometry of space-time. The minus sign in front of the space terms, that's what makes time different from space. And that C, that's what sets the relationship between them. Here's the really beautiful part. In this geometry, there are paths where T2, X2, Y2, Z2 equals exactly 0. These are called null paths, or light-like intervals. And anything that travels on these paths, photons, gravitational waves, anything with no mass, has to move at exactly c in any reference frame. Not because there's something special about light, but because that's what the geometry of space-time demands. So when we say nothing can go faster than light, we're really saying something much more profound. We're saying that the structure of space-time itself has this built-in speed limit. And it's not really about speed at all. It's about causality, about cause and effect. Here's what I mean. Imagine you're at point A in space-time, a particular place at a particular time. Now, could you do something at point A that affects what happens at point B? Well, that depends on how far apart they are in space and time. If point B is far away in space but close in time, so far that light couldn't get there, then no, you can't affect it. There's no way for the cause at A to reach the effect at B without going faster than C. And the geometry of space-time simply doesn't allow that. This is why we sometimes call C the speed of causality. It's the maximum rate at which cause and effect can propagate through the universe. If you could go faster than C, you could affect things in a way that would look like going backward in time from some other observer's perspective. That would be a mess. Causality would break down. You could have effects without causes, or effects that precede their causes. The whole logical structure of the universe would fall apart. So nature prevents this by making it impossible to go faster than C. And the way it does this is remarkable. As you try to go faster and faster, getting closer to C, something interesting happens. Your mass, or really your energy, appears to increase from the perspective of someone watching you. The faster you go, the more massive you become, which means you need more and more energy to go even faster. As you approach the speed of light, your effective mass approaches infinity, which means you need infinite energy to actually reach C. That's impossible, so you can't get there. But photons, particles of light, they have no rest mass, zero. So they don't have this problem. They don't have to accelerate to reach C. They just always go at C. From their perspective, if a photon could have a perspective, no time passes at all. A photon emitted from a distant star billions of light years away experiences no passage of time between when it's emitted and when it hits your eye. From the photon's point of view, the journey is instantaneous. Of course, we observe it taking billions of years, but that's because we're not the photon. Now, let me address something that confuses a lot of people. They hear that the speed of light is constant, always the same value c, no matter how fast you're moving. And they think, how can that be? If I'm running toward a flashlight, shouldn't I measure the light coming at me faster than if I were standing still? The answer is no, and here's why. When you start moving, you don't just change your velocity through space. You change how you're moving through space-time. Your notions of simultaneous change. Your measurements of distance change. Your measurements of time change. All of these things adjust in exactly the right way so that when you measure the speed of light, you always get c. This isn't a coincidence. It's not that light knows to adjust its speed to match what you'd measure. It's that the geometry of space-time is such that c is invariant. It's the same for everyone. The thing that changes is your measurement of space and time. Moving clocks run slow. Moving objects appear contracted. These aren't optical illusions or instrumental errors. They're real consequences of the fact that space and time are not absolute, but are part of a unified space-time with this Lorentzian geometry. Let me put it another way. Remember I said c is like a conversion factor between space and time. Well, what if we just used the same units for both? What if we measured time in meters, the distance light travels in that time? Or measured distance in seconds, the time it takes light to travel that distance. In those units, c would equal 1. It would be dimensionless, just a pure number, 1. And in fact, that's exactly what theoretical physicists often do. We set c Tafir 1 and work in what we call natural units. In those units, time and space have the same dimensions. A time interval of 1 second is the same as a distance of 300,000 kilometers. They're just two ways of measuring the same thing, intervals in space-time. When you think about it this way, asking, why is the speed of light constant, is like asking, why is the number 1 constant? Or, why does 1 kilometer equal 1,000 meters, no matter how fast you're moving? It's constant because it's a definition, a fundamental part of the structure we're measuring. But now you might be wondering, okay, fine, but why does the universe have this structure? Why is space-time Lorentzian rather than Euclidean? Why is there this speed limit at all? And that, my friends, is a much deeper question. I can tell you that our universe wouldn't make sense without it. If there were no maximum speed for causality, if causes could affect effects instantaneously, no matter how far apart they were, then the whole notion of locality would break down. What happens here would depend on what's happening everywhere all at once. There'd be no way to isolate systems, no way to do physics the way we do it. Moreover, if there were no invariant speed, there'd be no natural way to connect space and time. They'd be completely separate, and the symmetries of physics would be very different. The laws of electromagnetism, for instance, wouldn't work. Maxwell's equations, which describe how electric and magnetic fields behave, are built on the assumption that electromagnetic waves travel at c. If c could be different for different observers, these equations wouldn't be consistent. So in a sense, the existence of an invariant speed, what we call the speed of light, is deeply connected to the very possibility of having consistent laws of physics. It's connected to the structure of causality, to the relationship between electricity and magnetism, to the equivalence of mass and energy, E equals mc squared, right? And to so much more. When Einstein figured this out, he didn't start by saying, let me assume light goes at the same speed for everyone. He started by taking seriously two things we'd observed. First, that the laws of physics should be the same for everyone moving at constant velocity. And second, that Maxwell's equations describing light seemed to work for everyone. When he worked out the implications, he found that space and time had to be flexible, had to transform in this particular way, and that there had to be this invariant speed connecting them. The fact that light travels at this speed is almost secondary. Light happens to travel at c because it has no mass. But even if light didn't exist, even if photons didn't exist, c would still be there in the structure of space-time. It would still be the maximum speed of causality, the conversion factor between space and time, the fundamental geometric property of our universe. You could imagine a universe without light, without photons at all. Would we still discover this speed? Yes. We'd find it in the behavior of gravitational waves. We'd find it in how particles with mass behave as they're accelerated to higher and higher speeds. We'd find it in the structure of causality itself. We might call it something different, maybe the speed of causality, or the maximum speed, or just the invariant speed, but it would be the same c. So when you hear people say, nothing can go faster than the speed of light, I want you to translate that in your head. What they really mean is, nothing can go faster than the maximum speed allowed by the causal structure of spacetime. Light just happens to go at that speed because that's what massless particles do. And here's one final thing that really drives it home. You know how I said that as you move through space, you move more slowly through time? Well, there's a symmetry to this. From the perspective of someone else moving relative to you, your time is running slow, but their time is running normally from their perspective. This seems like a contradiction. How can both of you think the other one's clock is running slow? The resolution is that at the same time means different things to different observers. What you consider to be simultaneous, events happening at the same time, is different from what I consider simultaneous if we're moving relative to each other. The relativity of simultaneity is a direct consequence of the fact that c is invariant. And this ties everything together. Space and time aren't absolute, they're relative to the observer. But space-time, the unified whole, has an absolute structure, and that structure is characterized by c. The speed of light isn't about light, it's about the geometry of reality itself. I'll leave you with this thought. Every second of your life, you're traveling through space-time. Right now, almost all of your motion through space-time is in the time direction. You're moving forward through time at very close to the maximum rate. If you were to start moving through space, if you got up and started walking, or got in a car or a spaceship, some of your motion through time would be converted into motion through space. You'd age a tiny bit slower than someone standing still. At everyday speeds, the effect is impossibly small, but it's real, it's measurable with precise clocks. And if you could somehow move through space at close to c, nearly all of your motion through space-time would be in the space direction, leaving very little for the time direction. Time would slow to a crawl for you relative to the rest of the universe. At exactly c, which you can't reach if you have mass, but which photons do, all motion is through space and none through time. No time passes at all. The speed of light, this thing we call c, it's not telling you how fast light goes. It's telling you about the exchange rate between space and time. It's telling you about the shape of space-time. It's telling you about the maximum speed of cause and effect. It's one of the most fundamental properties of our universe, and it would be there even if light didn't exist. That's what I want you to take away from this. The speed of light is misnamed. It should be called the space-time constant, or the causality limit, or the invariant speed. but we're stuck with speed of light because historically that's how we first measured it. We noticed that light always seemed to go at the same speed, and we wondered why. And figuring out